the direction.
Yeah.
It's totally obvious. So.
In this particular topic,
Mm-hmm.
direction usually is much more confusing than calculating magnitudes.
Yeah, I found that.
Which part is it?
Homework part 2.
Part 2. And which problem?
Number 8.
So you have no question about 7?
No, I was able to figure that one out. Number 8.
Yeah, this one is interesting.
Yeah.
All right, so let me make a copy. And so can you see the screen clearly?
Yes.
Oh, good. So we've got a coil, well, technically, yeah, a coil, 23 turns, loops. We know the size, and we know electric current, and electric current travels. So if we look at this picture, like face, this direction is clockwise.
Right.
Now, so this loop might rotate about the vertical axis this way or that way. And magnetic field, how does it point? Oh, here, that's magnetic field. So it's actually helpful to have some kind of a props that could represent important direction. So, for example, magnetic field, and I just mentioned today, we didn't have time to practice, it's going to be done tomorrow, that for electric current like that, we can assign the area vector. And the area vector, well, for all possible situations when we need to relate translational motion and rotational motion, we use right hand or right screw. So in this situation, the area vector points into the screen. But if we use this picture, we can say the area vector points in the negative z direction.
Yeah.
Now, how does it affect the motion of the loop? The problem is this is not the best point of view, because I could draw a vector, area vector, like this, for example, but it doesn't really help to see what should happening. So we should turn this whole picture. Imagine that we could take it and turn it like that. So we would look like straight down. What would we see? And well, I would like to give you like half a minute. Try to imagine and draw a picture. If you would be looking straight down, what would you see?
I mean, it would kind of, you would see the top portion of the loop, and the current would be going towards the right.
Yes, and what about vectors A and B? A represents the area vector and B represents magnetic field.
So the area vector is perpendicular to the loop.
Well, it has two perpendicular directions, so up or down?
Up.
Exactly, very good. And what about magnetic field vector?
The magnetic field vector is 30 degrees below the horizontal.
Well, this is magnetic field, so, but technically we only need one arrow. So now, again, we didn't talk about it today, but if we would calculate, well, we could start from calculating force acting on each side and then torque, because, well, we could, there is a result, no matter how many times we do it, if we would let this loop or coil move freely from rest, it always moves in such a way so area vector wants to become parallel to magnetic field.
Oh, okay.
Because as we learned today, we have two extreme situations for a loop in a magnetic field. When magnetic field and area vector are perpendicular, that provides maximum possible torque acting on a loop.
Mm-hmm.
But when magnetic field and area vector are parallel or anti-parallel, that provides zero torque. And naturally, everything wants to get to the easiest situation.
Mm-hmm.
Now, on its own, that's very important, because technically we have two possible options to get these arrows parallel. But of course, again, natural, it would go through the shortest angle. So again, that all could be proved by just calculating torque, total torque. That's a good exercise, but we don't have to do that if we just remember that always we get to this.
Right.
So if we keep looking straight down, we would observe that this coil would start moving clockwise. This actually what we would say, well, torque and also angular velocity and also angular acceleration, because it starts from rest. And this is the direction which you need now to translate from rotational into translational again.
Mm-hmm.
And for that, you have to use again the same right-hand rule. For the clockwise motion, we assign a direction, the thumb, which points into the screen.
Okay.
So this will be the direction of the torque. Even in PY105, we had two different descriptions, clockwise or into, counterclockwise or out.
Mm-hmm.
And in this problem, it wants the final answer in terms of direction, into or out, but then, or it has to be described relative to this one of these axes, X, Y, and Z.
Mm-hmm.
So you have to go back and draw an arrow that would represent this into direction.
Mm-hmm.
So you have only 6 possible options: positive X, negative X, positive Y, negative Y direction, positive Z direction, and negative Z direction. Which of these represents into the screen?
So into the screen normally is negative C, but this problem, the correct answer is negative Y. So are you looking into from our own drawing?
No, you're looking at this correct, but my picture actually missing X, Y, and Z, this picture missing
Right.
X, Y, and Z axis. So in this picture, this would be X, right?
Yeah.
And how would Z point?
Z would be 90 degrees below, so it'd be down, right?
That would be Z. And how would Y point?
Into. Oh, okay.
No, Y would point out.
Out, and then negative Y is into.
So for this picture, into means negative Y.
Oh, okay.
So this always depends on specific point of view.
Okay. That makes more sense. I think intuitively, I didn't realize that it would want to rotate towards that. Like
because we didn't discuss that, but we discussed like a preview for that, because if you have a loop in a magnetic field, technically you always could calculate force acting on every side of this loop. You can, because we've done it. And then technically, because we have a specific axis of rotation, you can calculate for each force torque relative to this axis, calculate the net torque, and see what's going to happen. Technically, it's possible. The good thing is, no matter how many times we do this, we always get this rule that if we have a magnetic field and a loop with a given area vector, anything else doesn't matter. If you let it go from rest, it always will move in such a way so area vector wants to become parallel, because it always wants to get to zero torque, from not zero to zero. It's like sliding down a hill, a ramp.
Right. Okay, that makes sense. Okay. And then I also had a question on the practice problem set, the first problem set. And it was number.
Do you need to read it, or you can tell me?
I think I could tell you. Okay. So it's an equilateral triangle composed of 3 wires. So like each wire is either going into or out of the screen at each point. So the top one, it's coming out. I number 2, which is the bottom left one, is going in.
Okay.
And the last one is also going in, and that's current number 3.
So are they the same or different?
They are different. So current one is 4.6 amps. Current 2 is 9.2 amps. And current 3 is 18.4 amps.
And what are we looking for?
So you needed the magnitude and direction of the, I guess, the magnetic fields, like in the center of the triangle.
Net magnetic field.
Yeah. And I was able.
Here.
I was able to calculate the magnitude, but the direction I'm confused about. Because it asked for the direction counterclockwise from the x-axis.
Okay, but if you calculated the magnitude, that means you see the vector.
Right.
Well, in this situation, what we get? We get so the field number 1 points to the right. It has to be perpendicular to magnetic field line, which is a circular. I mean, tangential to magnetic field line, or perpendicular to this radius. The radius will be this distance will be the same for all of them, right?
Correct.
And so number two perpendicular, and that's going to be at 90 degrees. This is B2. So technically, probably you need to do components, right?
Right. I think. Am I looking at the same problem? Did I do this wrong? Maybe no. I'm second guessing my own work.
What? I drew what you told me. So
yeah.
Here,
I'm looking at
magnetic field points like this. This magnetic field number 2 points like this, and magnetic field number 3 points
right.
like that.
I think I might have just mislabeled one of the vectors, which is not surprising for me.
So this will be B3,
Yeah.
also at 90 degrees to
Yeah.
the radius. So, and from this point, because technically it's a geometry, calculate the magnitude is simple, right? You just do this. But then geometry, so you need the angles, and you need to calculate components, and then you add components. And when you add components, you get net field. How should it point? Well, I can guess. So it should be B1 plus B2 plus B3. So something like this.
Okay.
So I would guess, and calculation should give you two positive components. So your net magnetic field should look in this case like this.
Okay.
And that should be X component of the net field, Y component of the net field, and that's the angle you need to calculate. It will be measured already from positive X direction.
Right. Okay. I think I'm gonna double check my math. I guess Claire wants to go.
Okay.
All right. Thank you.
You're welcome. Is there anyone else?
Hi.
Hello.
I am doing homework to part 2, question 3.
Okay.
And I was able to figure out part A, but I'm struggling with part B. So I was hoping we could just go over that.
Oh, come on. Too large, too small. Just a second. So where am I? Here. And we need to calculate, I guess, net magnetic field. So at first you need to calculate magnetic field in the middle, and you did that. So now you need to calculate magnetic field at a different point. Well, okay, actually I need to shift it this way. And did you draw a picture?
Yeah.
How does magnetic field of the first wire point at point P in your picture?
It points upwards.
What rule did you use?
I used the right-handed rule, and then I drew circles to represent the magnetic field.
Well, in that case, you wouldn't get upward. If you have a circular magnetic field line, let's say this magnetic field line for the first wire, first of all, what direction should I choose? Clockwise or counterclockwise for this magnetic field line?
Clockwise.
clockwise, because this is how we use the right hand rule, correct? But here, at this point, you need to draw a vector that only touches tangential the circle, but in the same direction. So how do you draw a vector like that? How does it point?
To the right.
To the right. We also have a hint because it's a circle. If we draw a radius, the vector should always be perpendicular to it.
Oh.
So this is B1.
Yeah, I think I messed up. I actually said it was to the right.
Okay. And now we've got another vector. So we have to again draw a radius. Oops. Because it's much easier to use a 90 degrees angle. Now again, because it's same direction, but here the vector should be perpendicular.
Mm-hmm.
We actually don't know if it's stronger or less. The current number 2 is stronger, but distance also longer, so we don't know. But what we know is this. This will be vector B. So, at first, of course, we need to calculate the magnitude. 1, 2. And you did that probably. So, this times current number 1. Well, you've got different numbers. By the way, 2 pi and d. D will be the distance from the wire number 1 to the point. Here, we should use a different current and a different distance. So if this is D and this is D, this should be R2. Pythagorean theorem gives D squared of 2. So these are magnitudes. Starting from this, we are done with PY106. We have to go back to PY105 because we need to add 2 arrows. This is the first arrow, and this is the second arrow. And for each arrow, we know length and direction. So for example, what should be the angle for this arrow measured from horizontal? This angle. If you're not sure, it means you need to draw a better picture, bigger, clearer. This angle. I don't know, theta.
So you can find using like the length of the bigger triangle.
Well, we know it's D times square root of 2. What is this angle equal to at the base?
One over root 2.
Well,
or inverse sine of 1 over root 2.
Well, what is the number, the angle?
45.
45 degrees. And this is 45 degrees. And this is 90 degrees. So now starting from this, you should be able to say what theta is equal to.
45.
45, oops, absolutely right. 45 degrees, see? So now, again, you have to go back in time and use the component method. Because if you're calculating net field, we've done it before, your resultant B net, well, this plus this equals this is B net, will have two components, B net X equals B1X plus B2X. B net Y equals B1Y plus B2Y. So, good thing these are simple vectors. So X component for the first field is just the field. It has no vertical component. There is no, but components X and Y for B2 are equal because it's a 45 degrees angle. And that's going to be magnitude times sine or cosine of 45 square root of 2 over 2. So now you need to finish calculation and calculate two components of the net field. So for the net field, you will have in the end an arrow, B net. It will have a known X component, which is again B1X plus B2X. It will have a known Y component, which is again 0 plus B2Y, which is just B2X again, because they're the same. And then you can use what? Pythagorean theorem. Square root. And this angle, I don't know, alpha, you can find it using sine, cosine, or tangent. It's up to you. The result will be the same. This is the strategy. And with your values, you should get your numbers.
Okay. I think that answers my question.
I just want to check. So in the middle point, you would have B1 pointing down clockwise, but B2 pointing up. So to calculate net field, you would have to subtract these magnitudes, right? That's okay, just checking.
Yeah, that's how I did that one.
Okay. So when you see when the vectors parallel or anti-parallel, we just add or subtract things. But if vectors, may have any direction, in that case, we have to go back in time and use the component method. I guess I need to remind tomorrow, just in case. I will. Okay. So please just use the numbers, calculate, it should work.
Okay, thank you.
You're welcome.
Okay. Hi again.
Welcome.
So I just did the calculation for number 9 with the equilateral triangle, and it's weird because now I got like using the right vector for the top one, because I had originally done the calculation with all of them as going into the page, and I got the right magnitude, and then I did it correctly with the top one going out of the page, and I got the right angle, but not the right magnitude. So I'm a little confused.
Which problem is this?
Problem number 9. It's the one that we worked through, the one that I read out to you. But yeah, that one.
Well, I don't know what is happening.
Mhm.
I would have to just solve the problem with your numbers and see what I get.
Okay. Which, if you don't want to do that, that's fine. I was just like,
Well, if
I
no
thought
one
we
else
had
is waiting,
pre-
I can do that.
okay. Thank you.
Are we alone or somewhere else?
Mhm.
Is anybody else there?
I don't think
No.
so. It's just me.
Okay, so we can do that. And for that, what do I need to do? I need to go back to the slideshow.
Yeah.
I just want to use again the new slide.
Mhm.
So we've got out, in.
Mhm.
1, 2, 3. Out, in. We know X, X, X.
Mhm.
So many crosses.
Yeah. And
So
that's
I1 equals
4.6
4.6 amps, I2
is 9.2 amps,
9.2, and I3
18.4.
18.4. Such inconvenient numbers.
I know.
And X equals what for you?
10.5 centimeters.
10.5 centimeters, which is 0.105 meters.
Mhm.
And we need this distance, R.
And then, oh, I have that for you. It's 4.45
You sure?
positive.
All right.
Let's see.
4.05 centimeters. Well,
The 4.54, but 4.55.
this is basically this. So this is supposed to be 30 degrees.
Yes.
So a half of x over r should be equal to cosine of 30. So r should be equal to x over 2 cosine 30, which is in centimeters 10.5 over 2 cosine 30.
Oh, really? I had done 10.5 times the sine of 60 divided by 2.
Well, I'm using triangle, which
Yeah.
has a half of x, r, and this side, and this angle is supposed to be equal to a half of 60.
Right.
Because all these angles are 60, and this is a half of it, so 30.
Yeah.
And if I divide the side over hypotenuse, I should get the cosine of 30.
30.
So this is what I'm doing.
Would I be able to calculate it like the way I did though? Knowing that the hypotenuse, say, like if we drew a line bisecting the triangle, we knew the hypotenuse was 10.5. We knew that the angle was 60 to find that side. Interesting.
Well, I got a different number. I got 6.062 centimeters.
That's what I look at.
So, did you use a bigger triangle like this?
Yeah.
Well, and what did you do next? This is not a half.
Oh, okay. I think that may be where my confusion was. Okay.
This should be longer than this, I believe.
Oh, okay. I hope that's not my, okay. That might be my issue.
Well, that is an issue. It's an easy fix. It's just a distance.
Right.
And that probably doesn't affect the angles because it's like a like triangle. You enlarge a triangle or you make it smaller, angles remain the same.
Right.
But it definitely should affect the magnitude.
Right. Okay. Huh. All right.
Well, back to the drawing board.
Yeah. That might be.
That should be this, I believe. If your angle was correct and magnitude was not correct,
Yeah.
I believe this is the reason. Just
Okay.
basically, in all your calculations, you should divide by 4.54 and multiply by 6. This is your kind of factor, conversion factor.
Okay. So let's see.
Oh no, multiply by 4. Yeah, because equation for the field is 1 over r.
Mhm.
So you used 4.54. So you need to multiply by 4.54 and then divide by 6.062.
Yeah, and that gets me the correct answer. Okay. Thank you. So it's not the physics per se, it's just the math.
Geometry.
Right. All right.
Which
Well,
is
thank
fine.
you.
Which is fine.
Yeah.
Okay.
Thank you so much.
Yeah, no problem.
Take care.
Bye.
Bye.
Anyone else? I don't think so.
I got a magnitude, right? It was just the